Alright, so the next thing that I want to talk about is the broad concept of SLAM, which stands for Simultaneous, Localization, and Mapping. We've worked with mapping a bit in the current homework as I film this, and one of the things that is going on in the starter code for that homework is that we have a localization sensor, a position sensor that tells us where we are, x, y, and angle on the map or in the world, but it's provided with a certain amount of error. And it's error with this sort of like awkward error model where things drift around relatively quickly, and that's more or less difficult to correct for. We determined that having an error in angle was super obnoxious, and so we patched that out. But in practical robot control with physical robots, figuring out where you are is actually kind of a hard problem. Now, the thing that you'd like to do is, it would be really nice if we could just use GPS, right? If we could just have some way to have a sensor on our robot that would tell us where we are. And if we are outdoors and working on a relatively large scale, then GPS actually works fine. For a self-driving car, GPS will tell you what road you're on and which direction you're going and where on the road you are, and it does it well enough that you could even like take highway exits and stuff, especially if you have a little bit of sensor stuff that lets you see road lines. Even things like having a robot lawnmower that's going to mow a relatively large lawn, we can do our localization pretty accurately with GPS. Unfortunately, if we want to work on a relatively small scale, where we have the entire region that we're working with is a couple of meters square, GPS isn't really precise enough to tell us where we are. Even with a super expensive GPS, it's hard to get location more accurate under ideal conditions than like 10 centimeters. And working with GPSs that are like a reasonable price, like if we want to use the GPS on a cell phone as our GPS sensor, we're talking about 3-meter error, and it's error that isn't necessarily as convenient as like the error model in the homework where we're doing mapping, because it's the result of all kinds of nonsense like multipath bounce of the radio signal, and just modeling it's no fun. It's actually kind of funny. I did an experiment at one point with GPS localization where I had a robot with one $30 USB GPS on it, and that would let me figure out where the robot was to within about 4 meters, which wasn't useful enough for what I was trying to do. But mounting a second USB GPS on the robot about 2.5 feet away, and then averaging the two results, got my practical GPS error down under 2 meters, which was good enough. And that's just because the difference in location, having the two GPSs mounted a couple feet apart, was enough to produce different error because we got different multipath bounce. At least that's what I think was going on. It was two of the same model GPS. It wasn't even different model GPSs. So really, I don't know why that worked, but it did, and the robot ended up doing the thing it needed to do. But we'd like to use GPS. But if we're working at a small scale, we can't, and if we're working indoors, we can't. GPS just doesn't work at all indoors effectively. So if we can't use GPS, the thing that we're stuck with is other sensors. And the first sensor that we have on most robots, and this includes the robot kit suggested for this class, I say most robots, I mean good robots, is wheel encoders. So these will keep track of how far the wheels have turned, and by keeping track of how far the wheels have actually turned, we can figure out how far the robot should have gone forward. And if we have a robot with if we have a robot that's doing sort of tank steer, as the robot kit that's suggested for this class does, and as the sample robot in the homeworks is doing, we can also figure out how far the robot has turned. Now there's a little bit of problem with wheel slip, that as you rotate a robot with tank drive, the wheels have to slip to make that work, which means that you have to sort of estimate how much slip happened based on stuff, and you don't necessarily get correct information because it depends on what surface you're driving on. But wheel encoders still potentially give you really useful information, and optimally would tell you exactly how far you had gone. The problem is there is some error, and it ends up being a lot of error, especially if we're doing tank steer and turning. And those errors add up. There's no mechanism here with just encoders for us to ever recover from having added errors together. The errors will build up over time, and then we'll just have a big error. So just trying to use something like wheel encoders is a technique called dead reckoning. We're going to have the robot have some internal relative data about how it's moved. We add up the relative data about how it's moved and figure that the robot is at the position that's sort of the sum of the vectors of how we think it moved. And that's okay, but it necessarily has this cumulative error. It turns out this is enough to relatively accurately target cruise missiles. But on the other hand, with cruise missiles, you have much more expensive sensors than we have. Now, it turns out that cruise missiles don't have wheels, so they can't use wheel encoders. They use something else. The thing that they use is accelerometers. And that's going to measure how the robot has accelerated. Now that doesn't sound terribly useful. That would tell us what speed we're at, but that's not great. But the derivative of acceleration is speed, sum of speed over time is position. And so this gives us another source that we can use to try to determine position based on where the robot started and then what our estimates of its motion are. Now this has the same problem as wheel encoders, but just like I suggested happened the time I was playing with multiple GPS sensors, if we have different sources of data that both are trying to tell us the same sort of thing, we have wheel encoders that are trying to tell us how far we've moved, and we have accelerometers that with a little bit of math tell us how far we've moved. And then we've got another sensor that is potentially really accurate, and that's a magnetometer. Can be used as compass to get heading. And that works best outdoors, away from big chunks of metal, but you still get reasonably accurate magnetometer readings indoors. And I think that our good friend the robot kit has a magnetometer in it as well. I'm not 100% sure, but I'm pretty sure we have one. And once we have this many different sensors, and the magnetometer is nice in that this is a globally correct reading. There's some error, but it doesn't add up. If we sort of move the robot, turn the robot, and take another compass reading, it's going to be another reading based on reality with some error. So combining these sensors together, once we have this many sensors, we can start to get some better results. And there's a couple different ways to combine them. The classic way to combine these kind of sensors to try to produce a right answer is something called a Kalman filter, where we're going to do some prediction combined with the values that we got from multiple sensors, and that'll give us a better sort of result than just sort of blindly averaging together these numbers. And when you have multiple sensors, and including a accelerometer, and you feed them together into a Kalman filter, you're building something called a IMU, or inertial measurement unit. And at that point, you can start to get reasonably accurate information about how you've moved, and you can get pretty good dead reckoning. So we can get angle pretty good, but we still have this sort of cumulative error on position. And this sort of cumulative error on position is why the model in the mapping homework has a sort of position relative error. This is it was trying to be the same sort of error that we get with just summing up wheel encoders and accelerometers, although it's not quite a good model. But there's a trick that we have on robots that we can use to do better than this, and that is that we have more sensors. And the three sensors that are reasonably common on this sort of mobile robot, like rover-style mobile robots, is, optimally you'd like to have a LiDAR sensor. We have one in the simulation, but we don't have one in the physical robot. But similar to LiDAR is a sonar, which sort of gives us one point directly in front of us. And then another sensor that's pretty easy to get, pretty common, is a camera. And one of the things that I'd like to suggest doing with the physical robot is mounting a cell phone on it. Because if you mount a cell phone on the physical robot, that immediately gives you a camera. It immediately gives you a relatively high power CPU directly on the robot. You can plug in from the camera to the robot by USB if you pick up the right USB cable. And then then you have a camera and a powerful control computer. You also get yourself another accelerometer and another magnetometer that you could average into your position information or filter into your position information. But most importantly, the camera and the CPU. But once we have any of these guys, we can start to do this SLAM thing. So, because any of these three things gives us information about obstacles that we can use to build a map. And once we have a map, we can try to figure out where on the map we are by looking at the current sensor data. So the sort of easiest way to think about this is with a LiDAR. So let me go ahead and let me quickly start up just a random thing that has a LiDAR here. I'm starting up Gazebo in the background. And we can see here that we have our robot. There's no control program running, but we have a robot. And it is shooting out lasers. And based on the sensor data, as it is in this example, let me zoom in a little more so it's clearer, we have one laser hit. And knowing that we have one laser hit and that the laser hit is at this distance limits the set of possible positions that we're in. If we are, if we have some prediction of our position based on our other sensors, and for example, the the prediction was that we're right here, where the mouse is, we can say that prediction is definitely wrong, because if we were here, then that left-hand laser reading would be half of what it actually is. So we can use that to improve our position estimation. Another thing that we can do is we can use our laser information to validate things like our predicted speed. If we make the assumption that walls aren't moving, and we are driving forward in a situation like this one, we have the exact distance to the obstacle in front of us, and the obstacle in front of us isn't moving. And so if we think we moved forward, 1 meter per second for half a second, and our laser reading changed by 0.4 meters, we know that our estimate of half a meter per second for 1 second, or sorry, 1 meter per second for half a second is wrong. If half a second went by, we know that actually we were moving at 0.8 meters per second, because that's the calculated result we get if we figure out how much closer the obstacle got from our entirely accurate laser sensor. And if we have a sonar, same thing. It's not going to give us quite as good a reading on how far away the obstacle is, but whatever error bars we're putting on our sonar reading, that constrains the possible speeds that we've moved, and therefore the position that we're at, etc. So this idea of this is two separate ideas. So we have the idea of using our range information, our obstacle location information, immediately to constrain our movement estimations. So in that case, the laser range that we have can be used to constrain our estimate of our speed, or to directly indicate our speed when we're able to do it, which then may update our estimate of how accurate our encoders are. But we can also take advantage of our mapping information to then try to figure out where we are on the map. So the other trick that we have for combining sensors is something called a particle filter. A particle filter is a really neat idea where we start knowing our position on the map. And then based on the sort of probability distributions of how we're moving over time, we put down additional guesses as to our position on the map. And then we compare the guesses, all of the guesses. So imagine we're drawing dots on the map. We start with one dot on the map, and then as we move, we put down more dots based on the information that we have predicting what we're doing, and different sort of probability curves of what may have happened. And then for every particle that we've put down on the map, we go ahead and check it against the information that we have. What does our laser rangefinder say? What does our compass actually say? Etc. And we throw away the particles that sort of worst match the data that we have. And so then we end up with a bunch of estimates about our position, and we'll either end up with a cluster of particles that we can then use that as our actual estimate, or we'll end up with a ranking of particles and we use the best one as our estimate. But this is a method for trying to predict our location based on a bunch of different kinds of sensors. And I like this particle filter idea. I suggest considering looking into it more if you want to do this sort of a SLAM idea. So this problem of trying to figure out where we are on the map based on having a map that we've built and having some estimate of sensor data is sort of generically called a registration. And if we're not doing the particle filter idea, another thing that we can do is just go ahead and Imagine the robot being in a bunch of different poses, compare that to our instantaneous sensor data, and then take the one that matches the best. And some combination of these ideas will give us an estimate of position. So I mentioned SLAM specifically here in this location problem because some variant of solving this location problem is extremely likely to come up in any of the sort of rover-style robot projects you might be considering. With a physical robot, you're probably going to want a location estimate. With a virtual robot, you're probably going to want a location estimate. Solving SLAM in general is a good chunk of a project all by itself, and solving pieces of SLAM may be useful in any case. So yeah, definitely something that's worth considering. There's an entire course on SLAM on YouTube that I have linked to. I don't necessarily recommend watching the whole thing, but you may well want to watch the particle filter video because that's a good idea. So yeah, for your consideration.